Welcome to Digital Systems 2, and in this first video lecture we are going to discuss up-down, presettable, and IC synchronous counters. So by the end of the video, you should be able to create a counter that can count up or down, be able to create a counter that can be initialized or preset, analyze the operation of an IC synchronous counter, and decode any state of a counter. Those are our learning objectives in this video. Let's start with an explanation of a down counter. In the previous lecture, we talked about a synchronous up counter, and the synchronous counter has to use a clock signal that goes to the input of each flip-flop, shown here. And in order to have a synchronous counter, we also have to incorporate some AND gates in order for the counter to count properly. The one thing you'll notice about this particular picture is that it's a down counter, and it's going to count down because the output of each flip-flop now is being fed to the AND gate, and it's the inverse output from before. In the up counter that we discussed previously, the output of flip-flop A was what was connected going forward. The output of flip-flop B was what was connected going forward, flip-flop C and flip-flop D. With a down counter, you can basically use the same circuit setup as an up counter, but use the inverted outputs of each flip-flop. So notice how now the inverted output of each flip-flop is what is connected to what's going forward, as compared to the previous example in the previous lecture where an up counter was shown. If you look at the waveforms for a down counter, it'll look like this below, where the output of each flip-flop will begin at 1, 1, 1, 1, and then it will begin to count down from 15 down to 0. You can see that it'll continue to count down until this point right here. Here's where it's 0, 0, 0, 0, and then the reset point occurs right there. So that's how we can create a down counter, by using the same design as an up counter, but then connecting the inverted outputs of each flip-flop instead of using the regular outputs. An up-down counter is a counter that can be configured to count up or down depending on a control input. And on the screen you'll see an example of what a schematic for an up-down counter might look like. Notice we have a little bit more going on here. Let's start by looking at the inputs for each flip-flop. We can see that all flip-flops are connected to a clock signal, just like before. So this is going to be a synchronous up-down counter. We can see that the clear inputs of each flip-flop are all tied to 1, as well as the J and K inputs of flip-flop A. So we know that flip-flop A is always going to toggle whenever the clock makes a transition, because both inputs are tied to 1. But now if we look at the inputs to flip-flop B and flip-flop C, we're going to see something a little bit different. Notice that the inputs to flip-flop C are generated by an OR gate, and that OR gate has inputs coming from 2 AND gates, and the inputs to those AND gates are the output of flip-flop A, the output of flip-flop B, and a signal called up-down. Notice that the inputs to flip-flop B also come from an OR gate, and going into that OR gate is the output of 2 AND gates, and those AND gates have inputs from flip-flop A and up-down, as well as not A and the inverse of up-down. Notice it's connected to an inverter here. So for the first example, what we're going to do is analyze this counter and understand how it can be controlled to count up or count down. So we're going to begin with a truth table where we complete the inputs for each J and K inputs for all 3 flip-flops. And we're going to start with flip-flop C. So if you take a look at flip-flop C, whoops, we're going to zoom in here. Take a look at flip-flop C. J and K are going to be tied to this OR gate, and now we're going to ask ourselves, under what conditions would the output of this OR gate be high? The OR gate would only be high if A and B and up-down are all 1, or the OR gate will be high whenever A, B, and up-down are all 0. Because if you think about it, if A is 0, then not A would be 1. If B is 0, then not B would be 1. And if up down is 0, then not up down, because it gets inverted, would also be 1. So those are our three instances where we would have the output of the OR gate to be high. So as we fill in this truth table, we can see that we only have a few instances where J and K are both 1. That's when up, down, A, and B are all 1. That would make this AND gate high, which would then make the output of the OR gate high. Or if up, down, A, and B are all 0, then this AND gate would be providing a high, because all three of those will be inverted to give you a 1. Those are the only two instances where J and K would be receiving a 1 or a high from this OR gate. So we know that everywhere else within this section of the truth table will be a low. Next, we're going to apply the same line of thinking to figure out the inputs to the J and K inputs of the flip-flop B. Notice we have two AND gates to consider here, but each AND gate has less inputs. So for this particular piece of the circuit, I know that the OR gate will output a high if A and up down are high, or if A and up down are both low. So we have 4 instances where the inputs to our flip-flops will be 1. And those 4 instances will occur when up, down, and A are high, which occurs in these 2 rows here, or when up, down, and A are both low, which occurs in these 2 rows right here. So we have 4 instances where the input to the JK flip-flop will be 1. Otherwise, the input will be 0 because this OR gate will be providing a low to those inputs. Lastly, we can look at flip-flop A, and we can see that the J and K inputs are tied to 1. So that means those inputs are always 1. Now that we have a truth table to understand how this circuit is going to work, the next thing that we're going to do is create a waveform to demonstrate that output. And so if you look at what's given, we have some inputs. First, we have the input up, down, which is high at some point until it goes low. And based off of how this is labeled, we can see that if we want to count up, that's the active high state. That means whenever this input is high, we're counting up. And the over bar over the word down tells me that if I want to count down, that's an active low state. So I can't count down unless this signal is low, which will occur right here. So I have a critical point that I'm going to outline on the waveform before I even start drawing anything. That's the point right there where I'm going to switch from counting up to counting down. Keep in mind that before this point, the counter will count up. And it's going to start at 0. It's going to go up to 1, 2, 3, and 4. And it's going to continue counting, it's going to continue counting up until up down changes from high to low. And we're going to see that change happen right here. Now, up down is what we call a synchronous control input, which means it will take effect on the next applicable clock transition. It doesn't take effect automatically. So what we're going to see is that after this point, the next clock transition that occurs will cause the counter to now begin counting down. So we call that again a synchronous control signal. The effect of this signal doesn't happen until the next clock transition, which is right here. So what we're going to see is that after up down is switched from high to low, it's going to stay where it is right now until the next clock signal. On the next clock signal, it begins to count down. So 4, 3, 2, 1, and 0. And we can determine each one of these waveforms by using the truth table on the screen before. So for example, if I go back here, I can determine what the output of each flip-flop is going to be based off of up, down, and our inputs A and B. But ultimately, we're going to be creating a counter here that can count up or count down depending on the input up, down. When up, down is high, it'll count up. When up, down is low, it'll count down. And this is called a synchronous control signal, meaning the effect doesn't happen until the next applicable clock transition. In this example, we're responding to negative clock transitions because the flip-flops here have all been labeled with a bubble. That tells us they all respond to a negative transition. So this is how we would draw a waveform for an up-down counter, showing that it first counts up and then begins to count down. If you're a little bit foggy with drawing waveforms, just remember that the count is considered the outputs of flip-flops C, B, and A, where flip-flop C is the most significant bit, flip-flop A is the least significant bit. So as you draw your waveforms, the first digit in each one of these numbers is the waveform for C. 0, 0, 0, 1, 0, 0, 0, 0, and 1. So you're simply going to be creating a waveform to reflect the count as the counter counts up or counts down. So this is the waveform for an up-down counter, showing that example. A state transition diagram illustrates how the up-down counter changes states based on the input from up-down. When up-down is a 1, like here, when up-down is a 1, we count up. We go from 0, 0, 0 to 0, 0, 1 to 0, 1, 0, and so forth. When up-down is a 0, like here, we count down. For example, we might go from 5 to 4 to 3 to 2, and so forth. So a state transition diagram is a way to illustrate all the states of your counter, and the arrows represent how you go from one state to the next, dependent upon the logic level that is applied to your control input. In this case, that would be up, down. A presettable counter is a counter that can be set to any desired starting point, synchronously or asynchronously. And on the screen is an example of a synchronous presettable counter with an asynchronous parallel load. So let's break that down for a minute. It's a synchronous counter. That means that each flip-flop has a clock signal that is attached to the same clock input. Imagine a clock signal coming from your function generator. Each flip-flop has a single clock signal all coming from the same point. So it's considered a synchronous counter because of that reason. The reason why we call it a synchronous counter with an asynchronous parallel load is because I can determine the output of the counter using these three inputs. And if I were to apply three inputs, for example, I could apply a high and then a low and then a high right here. I can apply any inputs I want, and I can immediately force the output of the counter to take whatever input I select and apply right here anytime I send a signal to this parallel load input. And I can force the flip-flops to change their states automatically. Anytime you have an asynchronous input, the asynchronous input will have an effect instantly. A synchronous input will have an effect on the next applicable clock transition. So with an asynchronous parallel load, that means that I can load a number into my counter instantly without waiting for the next clock cycle to occur. And now we're going to sort of analyze how this presettable counter works and follow an example to see exactly how we can force the output of the counter to be whatever we want. So if you take a look at JK, the JK flip-flops for each counter, they're all wired as a synchronous parallel up counter. This is the same parallel up counter design that we've seen before. And as a reminder, each flip-flop has a preset and a clear input. Both of these inputs are active low. Active low. That means if I want to preset the flip-flop, or I want to force the output of the flip-flop to be high, I have to send a low signal to this input because it's active low. If I want to clear the flip-flop and force the output to be 0, I have to send a low signal to that input because it's labeled as an active low input. So with these inputs, I can't use them unless I send the right signal. They're both labeled as active low inputs, so I have to send a low to either one of these if I want to use that particular function. Keep in mind that pre and clear are asynchronous override inputs, meaning that if I apply a low to this signal here or to the signal here, the effect happens immediately, not on the next clock transition. That's what asynchronous means. The effect happens instantly. The way that this counter will work is that you'll load a value into the counter by first applying whatever value you want to P2, P1, and P0. So imagine those make up the digits of a binary number. So maybe I want to load the number 111 or the number 001, whatever number I want to load. I will literally apply a high or a low to each one of these inputs to construct that number. And then when I want the number to physically be loaded in, I have to apply a low pulse to the parallel load input, which is labeled as PL, a low pulse. So the parallel load input is also an active low input. You can't load it unless you send a low signal. It's an active low input. And now we're going to walk through how this counter works using an example. Let's say that we want to load the value 101 into the counter. That means P2 would have to be a 1, P1 would have to be a 0, and P0 would have to be a 1. And just imagine that we connect these inputs to switches, and we set the switches high or low depending on what we want the value of the counter to have. So when pulse load is high, these inputs have no effect. So I can change these inputs all day long. It really doesn't do anything until I physically load it into the counter using this input down here, the pulse load input. So if there's a clock present, the counter is just going to count as normal and these inputs will have no effect. But when we pulse this input low, we have to send a low signal when we pulse it low. Now we're going to see what happens to the counter step by step. So when our pulse load signal goes low, that means I'm sending a 0 in right here. Keep in mind our inputs are that P2 is a 1, P1 is a 0, and P0 is a 1. I want to load the number 101 into the counter. That's my goal. So once pulse load goes low, let's take a look at what happens step by step. The first thing that you'll see is that pulse load gets inverted right here. And the output of that inverter is being sent right here into this NAND gate. So I have P2 and the inverted pulse load going into this NAND gate. Or you can think about it as a 1 and a 1 going into a NAND gate. A 0 is going to come out of that NAND gate. And this 0 is going to be fed into the preset input of this flip-flop. Since that's an active low input, I'm going to activate that function, which means I'm going to preset the flip-flop and force Q to be 1. I'm going to force Q to be 1. So I've preset this flip-flop to be the value that was selected right here by the user. If we follow this logic along, we can see that P2 is connected here, goes down through an inverter, comes out here as a 0. So we have a 0 going into this NAND gate with a 1, which is the inverted pulse load input, the one that's coming out of this inverter. It goes in here. This 0 and this 1 go into the NAND gate, and a 1 will come out. So we can activate the pre-input without activating the clear input using this circuit diagram here. And you never want to try to preset and clear a flip-flop at the same time. That's contradictory. So it makes sense that if one input is 0, the other one should be 1. And remember, since this is active low, sending a 1 in here basically does nothing. It's like saying I'm not using this input. I don't want to clear the flip-flop. So there's no issue here. Next, let's go on to the next flip-flop. So remember that this PL, this post-load signal, gets inverted. It gets delivered here, and then it also is delivered right here. So post-load is a 1. P1 is a 0. That 0 and that 1 go into this NAND gate, and a 1 comes out, which means I'm not going to activate this input because it's active low and I'm not sending a low. So nothing happens here. Now if we follow this along here, P1 comes down here and gets inverted to a 1. A 1 goes into the NAND gate with the pulse load signal, which is also a 1. These are all connected. So a 1 and a 1 go into a NAND gate, 0 comes out, that 0 gets sent to the clear input. That clear input is active low. I'm now activating that particular function for that flip-flop, which means I'm forcing the output of the flip-flop to be 0. I'm clearing that flip-flop. And that output will now be 0. And then if we follow the same logic around to the third flip-flop, the post-load signal that we have has been inverted and is fed to this input as well as a 1. We have a 1 and a 1 going into a NAND gate, which is going to give you a 0. That 0 is going to preset the flip-flop and force the output to be 1. At the same time, your P0 input is being inverted and fed down to another NAND gate where it combines with your PL signal and giving you a 1 at the output of this NAND gate, giving you a 1 here. So you're presetting the flip-flop, you're not clearing it, thereby you have set the flip-flop to have the output 1, 0, 1. Now keep in mind that your counter has now been set, but it won't count until you return pulse load back high. That's why it's shown as a pulse. You don't set it low and leave it there forever. You set it low to load, and then you have to set it back high to allow the counter to count. So the counter will become preset regardless of what is occurring at the clock input as long as PL is low. It's like the clock has no effect. The count will hold at 101 until PL is deactivated, which in this case would mean PL has to go back high. At that time, the counter will resume counting up at each clock pulse, and it'll start from 101. So now let's do a timing diagram for a presettable counter. We're going to use the same circuit that was just discussed on the previous slide. And the initial condition for the counter is given in the diagram below. So I have 3 outputs, Q2, Q1, Q0. And right now the initial count for the counter is 0, 0, 0. So before we begin the waveform, it's more important to identify critical points than it is to just start filling this in. So let's identify some critical points. The first critical point is when the asynchronous parallel load happens, which is when PL goes low. Remember, that's an asynchronous input, which means we're going to load the counter immediately, not on the next clock pulse. Also remember that the counter can't count as long as this is low. So nothing will happen except that the counter will load while this is low. This has to return high for the counter to count. Not only does it have to return high, but the counter won't actually begin to respond until the next negative transition after this goes high. Once this goes high, the clock is now in control, and with this circuit diagram that you have, the flip-flops respond to negative edges. So once the pulse load input has released control and gone back high, the next negative edge is when the counter will begin to count. So I have that identified right here in green. Our other parallel load happens once again right here when pulse load goes low. And again, as long as this is low, no counting will occur. The only thing that can happen is the load. Once this goes high, we wait for the next applicable clock transition, and then it will begin to count once again. Now that we've identified these critical points, it'll be pretty easy to fill in the waveform. I know that up until the first red line, it should count as normal. It should count up. I know that between the red and the green, it should load the value 101. That's our data that we're loading in. It should load that value and hold it until the green line. After the green line, it will begin counting up from that value. And I know it's going to continue counting up until I hit the next red line where I'm supposed to load. The data that I'm supposed to load is right here. And between this red line and this green line, I'll know that I'll load that data and it'll hold until the green line is here, and then it'll begin counting up again. So if you identify your critical points first, it makes the waveform a lot more simple to fill in. So let's start with this piece right here. The counter is going to start at 0, 0, 0. It's going to count up 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. Up right until this point where we're going to load. And we're going to load the value 1, 0, 1. So between these 2 points, Q2 is a 1, Q1 is the 0, Q0 is the 1. This is your most significant bit. This is your least significant bit. So now I can tell from my critical point right here, this is when we begin counting again, and we're going to count up from 1, 0, 1. So the counter will go 1, 1, 0, 1, 1, 1. At that point, the counter will start back over at 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, and now we've hit another load point. That's an asynchronous load, so it'll happen immediately. We're going to load the value 0, 1, 0. And the counter will not be able to count until load has gone high and the next negative clock transition occurs, which is right here. And then it'll begin counting up once again from there. This is how we would do the waveform for a presettable counter. Remember to identify where your asynchronous parallel loads occur, and then identify when it will begin to count again after that point. Once you've identified those critical points, you'll use the data given here to know what to load. And basically, when you see that there's an asynchronous parallel load, it's whatever that data is at that point that you'll load. So notice that right here, the data changes from 101 to 010. So the next time we loaded the 010 right here. Other than that, if it's not loading, it's counting up. And this is how we do a waveform for a presettable counter. When you do Lab 14 in this course, you will be utilizing a presettable up-down counter. The part number is the LS74193. And this is the diagram for it and some of the pin names. We'll reference this again later when we get closer to the lab, but you will directly be applying the concepts we've just discussed in Lab 14, where you'll build a presettable up-down counter. Next, we're going to talk about IC synchronous counters. And these are counters that have already been developed for you to use off the shelf. So instead of getting a bunch of JK flip-flops and trying to wire your own counter, you can use an IC counter to count for you. There are a couple different types that we're going to discuss in this lecture. The first is the 74 ALS 160, 161, 162, and 163. These are 4 different part numbers that are all different types of counters. You can see over here that the 160 and the 162 have a mod of 10. It's a mod 10 counter. That means it can only count from 0 to 9. And then we can see that the ALS 161 and 163 are mod 16 counters. Those can count from 0 to 15. Each counter contains 4 flip-flops. The flip-flops are triggered by a positive going transition because there's no bubble on the clock input. They have an active low, synchronous clear input, and can be preset to any value by applying an active low load input, which is right here. Notice the bubble in the bar tells you it's active low. So I can preset the value of the counter by applying a value at D, C, B, and A. I can then send a low signal to the load input, and then the outputs of the counter will be whatever I want it to be based off of the inputs supplied to D, C, B, and A. So a few of these we've already discussed, but I'm going to go over each one of the inputs on the 74 ALS 160 to 163. You have your clock input, which goes here. You have 2 enables, and they're active high. So the counter will not count unless both of these are connected to a 1. You have your clear. It's an active low input. And depending on the part number, this will either be synchronous or asynchronous. And I'll show you a function table where we can determine which part numbers have which function. So this could be synchronous or synchronous, which will matter when you're drawing a waveform. We have an active low load. Depending on your part number, this can also be synchronous or asynchronous. I'll show you the function table in a minute to know which way this one is going to work. Then to preset a value, we have to apply a desired 4-bit value, DCBA, where D is the most significant bit, to these 4 inputs here. The outputs of your counter will be here, where QD is your most significant bit. And then we have this output here called RCO. RCO is an active high output that will detect or decode the last or terminal state of the counter. So if you're counting from 0 to 9, that would be whenever you hit 9, 1, 0, 0, 1. If you're counting from 0 to 15, that would be when you hit 1, 1, 1, 1 at your outputs. This is useful when we cascade several counters together to create a larger counter that can have a higher mod number than a mod 10 or a mod 16. ENT must be high to enable your RCO output. Next, we have a function table which explains one small difference between your 160, 161 and your 162 and 163. And it's the clear function. The 160 and the 161 have an asynchronous clear. The 162 and 163 have asynchronous clear. Remember, the asynchronous clear means it's going to clear the flip-flop instantly. If you activate that input, the flip-flop will clear instantly. With the synchronous clear, the flip-flop will not clear until you have the next applicable clock transition. And they all have a synchronous load, which means the counter cannot be loaded until the next available clock transition after you activate the input. After you activate that input, and that's an active low input as well. So let's look at an example. We have a 74HC163 that has the input signal shown below. The parallel data inputs are permanently connected to 1100. That's shown right here. Assume the counter is initially in the 0000 state and determine the counter output waveforms. So we have a lot going on here. The first thing we need to do is look at the part number we're given. Look at the function table that we're given and make sure that we know all the important information about this. One thing being, if it's a 163, it has a synchronous clear. Now we have to look at our inputs given and make sure we understand how the counter is going to work based off of these inputs. So the first thing that we're going to do is identify, once again, our critical points. before we draw the waveform, what are the important parts of this output that we really need to consider? Here's your first critical point, that there's a synchronous clear right here when clear goes low. The only reason how I know that it's a synchronous clear is because I used the function table on the slide before. So I know that the clear is going to happen at this clock transition right here. Not before, not after. It goes low right here, but it doesn't take effect until the clock makes a positive transition. So the clear is going to happen right here. I also have a synchronous load that occurs at this clock transition, labeled as T3. Even though load goes low before that point in time, because this is a synchronous input, it doesn't take effect until the clock makes a transition, which would be right here at T3. Also notice that you have two active high enable inputs on this chip. Both of these have to be high in order for the chip to count and have an output. Notice that ENP goes low at a certain point and then ENT goes low at a certain point. And basically in between these 2 points, counting is disabled because one of those is low. They both have to stay high for the counter to have its output counting, to have it enabled. So once both of these return back high, on the next positive transition, which is right here at T6, the next positive transition is when counting will resume. So now we know all the critical points, and we can determine the waveform beginning with the first section. The initial output for the counter was 0, 0, 0, 0. So we know it's going to begin counting from 0 to 1, 2, 3, 4, and 5 until the clear happens right here at our first critical point. So once that clear happens, we're going to see all the flip-flops set back to 0, 0, 0, 0, 0. And then it's going to begin starting to count over again with each clock pulse. So it's cleared out here, and on the next clock transition, it'll begin to count up from 0. Now we get to this point right here, where we're going to load. And what value are we going to load? Whatever value has been applied right here. So we're going to load 1100 into the counter. And you'll see that right here. 1, 1, 0, 0. And once we load, on the next applicable clock transition, it'll just count from there. So we have 1100, 1101, 1110. It's counting up once again. Right here is that area where counting is disabled. So I know that the counter is not going to change its output between this point and this point. It's stuck at 1110. And then once both of our enables go back high, on the next applicable clock transition, which would be T6, the counter starts counting up again. And this is how we would draw a waveform for the 163 given the conditions that were presented. Also, we have the RCO output. Remember, the RCO detects when you've reached your last state in the counter, and then it'll go high. So the last state for a mod 16 counter would be when you reach 1111. This goes high to indicate that you've reached the last state. Once the counter rolls back over to 0000, RCO will go back low. Two other kinds of IC synchronous counters are the 74 ALS 190 and the ALS 191. These are recycling 4-bit counters. They have similar inputs, but there are a few things that are different. First, notice the part number. The 190 is a mod 10. The 191 is a mod 16. So you'll always want to know your mod number so you know the value that it will count up to. Just because it has 4 outputs doesn't mean it's always going to go up to 15. Always review that. Next, we have the clock input, like we did before. And then we have a CTEN, that's a count enable input. It's active low. So this signal must always be low in order to enable the counter to count. Then we have DU, which is called up down, or down/up technically. It controls whether the counter counts up or down. Based off of how it's labeled, the D has no bar, so that's active high. So if I want to count down, I need to supply a 1. The U has a bar. Anything with a bar means it's active low. So if I want to count up, I need to send a 0 to this input. Load is an asynchronous override input, so the load happens asynchronously, immediately, not on the next clock transition. And then we have our inputs, DCBA, if you want to preset the counter, just as before. The outputs come out here, just as before. We have this output called max-min. Max-min will determine when the counter has reached its terminal state. And then RCO is an active low output here, and it's a little bit different. It will mimic the clock waveform when the terminal state is reached. So we have max-min and RCO, which work differently than the part number before. Next, we're going to do an example using the 74LS190 counter. So we have the 74-190. It has the input signals given in the diagram below. The parallel data inputs are permanently connected to 0111, which we can see in the diagram right here. Assume the counter is initially in the 0000 state and determine the counter output waveforms. So we're going to do another waveform, similar as before, except now we have the 190. Let's review. The 190 is a mod 10 counter, so it's only going to count from 0 to 9, no higher. We also can see that it has an asynchronous load, and we have this input, the up-down input, which will control whether it counts down or counts up. So as we do our waveform, we're going to start once again by identifying some critical points. The first critical point is when the load occurs right here. That's an asynchronous load, so it'll happen immediately. And the counter won't begin to count until load has gone back high and the next applicable clock transition occurs, which will be right here. Another critical point is when the up-down signal changes from low to high. If the signal is low, we're counting up, but when this changes from low to high, now and after this red mark, it's going to be counting down. That's a synchronous input, which means it doesn't take effect until the next clock transition, which would be right there. Also, notice that our enable, the CTEN, that's a count enable, that's an active low input, which means if we want the counter to count, that has to be low. So when it goes high, the count is disabled. No counting can occur when this input is high. Once it goes back low, it'll begin counting again on the next clock pulse. So these are some of our critical points that we're going to be aware of. Again, remember that the assumption is the counter begins in the 0000 state. So we have 0000, 0001, 0010, and so forth. It's going to start counting up. And here's the count. 1, 2, 3, 4, and so forth. As it counts, it'll get up to 0100. And then we have this load that occurs right here. It's going to load right at that point. So we're going to be loading the value that is supplied at the inputs, which is right here. So it's going to load 0111. 0111. And technically, it'll actually count from 4 to 5 for a split second before this load, because it gets to 0100 right here. Right here, it gets to 0101, which is technically 5, before the asynchronous load happens. I just didn't have space to fit that in. The load occurs right here, and nothing else can occur until that load signal goes back high and the next clock pulse occurs. After that point, we're going to continue counting up. So we loaded 0, 1, 1, 1, which is 7. After that comes 8, after that comes 9, and then we reset back to 0 because this is a mod 10 counter. It does not go up to 15, it only goes up to 9. Notice that because we reached the last state, max-min goes high right here when the output is 9. That's the last state. That's the terminal state. And during this point in time, RCO mimics the clock. Just like that. So as it begins to recycle right here, it'll continue to count up until now our up-down input has changed. And on the next clock pulse, now it's going to count down. So it went 8, 9, 0, 1, 2. Now it's going to count down. 1, 0, 9. After 0 comes 9 if you're counting down and you're recycling. Also notice that when we count down, now 0, 0, 0, 0 is the last state, the terminal state. When you're counting down, that's your last state. So we see that max-min goes high again to signal, hey, I've reached the last state, and RCO mimics the clock once again during that time. We can now see that the count is disabled right in here. So no change in the output here. And then once the counting is enabled again with this low signal, it will continue to count down. That's how the 74190 works. Here's another example using the 161. We're going to refer to this IC counter below. We're going to draw the state transition diagram for the counter's outputs, and then we're going to determine the mod number, and then we're going to determine the relationship of output frequency of the most significant bit to the input clock frequency. So here's a reminder of your function table for this particular IC. The 161 is a mod 16 counter, so it will count up to a maximum of 15. However, let's take a look at what's going on with the wiring here. I can see that QD is inverted and then sent back to this D input. I can also see that QC and QB are going through this NAND gate and being fed to the load input. The enables are all high, so I know it's enabled to count. The clear input is also connected to high, so I'm never going to clear it using that input. And we can see that the load is controlled by this NAND gate. So ask yourself, when will this load? It will load when C and B are both high. C and B are both high going into a NAND gate, the output will be low, the load input will load. And then what will it load whenever C and B are both high? It will load A, input A is connected to 1, inputs B and C are connected to ground, and input D is the output of this inverter. So let's take a look at how this counter will count. Let's just assume it starts counting at 0. So we have 0, 1, 2, 3, 4, 5, 6. Right here, B and C are 1. B and C are 1. It's going to synchronously load, which means on the next clock pulse, it's going to load. Again, what is it going to load? It's going to take output D and invert it and load that into input D right here. C and B will be 0, A will be 1. So the D gets inverted, C and B are 0, A is 1. That's what it'll load. And then it'll begin counting. So that's 9, 10, 11, 12, 13, 14. Here's the next time B and C are both 1. So we're going to load again. And when we load, we're going to invert D, and then B and C will be the same as before, as will A. So when we load, we actually end up loading 0, 0, 0, 1. And now we fall into a cycle where it's going to continue to count from 0, 0, 0, 1 through these states until it gets here and it does a load. Then it'll count until it gets here and does another load, and we end up in this infinite loop here. So once it's in the counting sequence, after the first synchronous load occurs, there are 12 states. 12 states total. So it goes 9, 10, 11, 12, 13, 14, 1, 2, 3, 4, 5, 6, and now I'm back where I started. That's 12 states total, so this makes it a mod 12 counter because it has 12 states. Remember, a mod 12 counter doesn't have to count from 0 to 11, it just has to have 12 states. The output frequency is related to the input frequency divided by the mod number. So if I know the input frequency for the clock signal, I can find the output frequency for the most significant bit by dividing it by 12. Many standard IC counters have been designed to make it easy to connect multiple chips to create circuits with a higher counting range. This is called cascading. For example, we have two 74 ALS 163s where the RCO input, the RCO output, becomes an enable input for another chip. So only when this counter has reached its highest value will the next counter be triggered to count. And by cascading our counters together, we can create a counter with a higher mod number. So instead of being able to count from 0 to 15, now we can count to something much, much larger than that by cascading these together. So here's an example where we're going to study cascading. So we have two circuits right here. They're both 161s. Notice that the output of flip-flop D is the clock signal for the second counter. And here's the question. The frequency of Fn, right here, is 6 megahertz. The two IC counter chips have been cascaded asynchronously, so that the output frequency produced by counter U1, that's this one, is the input frequency for counter U2. Determine the output frequency for Fout1 and Fout2. Determine the mod number of the entire circuit. So we have a lot going on here. We have two counters that have been cascaded. We also have one counter that's been modified with a NAND gate. We also have this counter that's been modified with an inverter. So we really need to break this down and understand what each counter is doing individually, and then figure out what they're doing collectively as a team. Let's start with U1. The counter on the left will count from 0, 0, 0, 0 to 1, 1, 0, 0. How do I know that? Let's take a look. QD, QC are being fed into a NAND gate. So when both of those outputs are high, basically when you have 1, 0, 0, 0, when both of those outputs are high, the output of the NAND will be low. The low will be fed into the clear inputs. It will asynchronously clear at that point in time, so it'll clear pretty much instantly. This means that the state 1100 is a transient state and does not count towards the mod number. So if it's going to clear instantly, this state doesn't really occur for more than a few nanoseconds, and we don't count it as part of the mod number. That means this counter will count up to 12, 1100. It will instantly clear everything out and start counting over at that point. So it's only ever going to count from 0 to 11. Once it gets to 12, it clears instantly, and that state doesn't count. This is a mod 12 counter. Now let's look at the circuit on the right. This counter on the right will count from 0, 0, 0 to 0, 1, 0, 0 and then synchronously load at that state. Let's take a look at how we know this. Look at the output here. When output C comes out, it gets inverted. And that is then connected to the load signal. So it'll count up until you get to the point where output C is a 1. That would be when you have 0, 1, 0, 0. So that 1 gets inverted to a 0. That 0 triggers a load. But the difference between the one on the left and the one on the right is that the clear is asynchronous. The load is synchronous. So the load that's going to occur is not going to happen until the next clock pulse. So that means that this counter counts through that state and then it'll load. And when it loads, it's going to load 0, 0, 0, 0 because all these are connected to ground. So for the counter on the right, we count this as part of the mod number because it's a synchronous load. On the left, we don't count it because it was an asynchronous clear. This is a mod 5 counter on the right. So F out 1 is going to be the input frequency, which was given as 6 megahertz, divided by mod number. That means there's a 500 kilohertz frequency that is feeding this counter. The second counter will have an F out of the 500 kilohertz going in divided by its mod number, which was 5. Lastly, the total mod number for the counter would be the mod number for the counter on the left times the mod number for the counter on the right, which would be 60. Digital counters are often used in applications where the count represented by the flip-flop states must somehow be determined or displayed. Typically, when we display the output of a counter, we just connect each flip-flop to an LED. That's one way to figure out, well, what's the count right now? Decoding a counter is the conversion of a binary output to a decimal value, a form that is immediately recognized. Typically, what that means is that we have one LED to represent one output. So let's say that I have 10 LEDs. We'll say that LED number 1 is representative of the number 1. We'll say LED 2 is representative of the number 2, etc. And what we would do to decode a counter is to have a series of AND gates connected to each LED. So that if I wanted the LED that represented the number 0 to turn on, I would connect not C, not B, and not A to an AND gate. Now keep in mind, not C, not B, and not A would be when the output of your flip-flop is 0, 0, 0. But if you invert those, you'd have 1, 1, 1. This AND gate would be connected to an LED that would light up letting you know the count is 0. Just one light telling you, oh, the count is 0. If you wanted to know when the count was 1, here's what you would connect to your next AND gate to represent an output of 1. And you'd have one light, just one light, that would come on when the count was 1. So how this works is you would label your lights so that you know which light represents what decimal number. And then you have an AND gate connected to each light that will light up only when the output of your counter matches the decimal number for that particular LED. That's called decoding a counter. So essentially, you're going to have an AND gate for each state. You're going to connect the inputs to each AND gate based off of what the count would be for each state. So when the count is 1, 0, 0, you're going to have an AND gate to represent that, where the inputs are going to be when C is high and you have B and A are low. This is what we call decoding a counter. And that is the end of this lecture.